Have you ever wondered how your money grows in a bank, how scientists measure earthquakes, or how fast a virus can spread? The answers all involve logarithms and exponentials, two fundamental concepts in math. In this video, I'll go over what logarithms and exponentials are, show why they're significant, and display some real-world examples. So what are logarithms and exponentials? Well, put simply, let's see it like this. Addition is the opposite of subtraction, since they're inverse operations. You can see that with 5 plus 3 minus 3 equals 5. And multiplication is the opposite of division, and since they're also inverse operations. You can see that with 6 times 2 divided by 2 equals 6. And exponentials are the opposite of logarithms, because they're also inverse operations. So here we see that y equals 2 to the power of x. Then taking the logarithm base 2 gives x equals log base 2 of y. Okay, and with their purpose and meaning, a logarithm answers the question, to what power must the base be raised to produce a given number? Now, what exactly does that mean? It means that y equals log base a of x, and what that means is that a to the power of y equals x. Let's see that with an example here. 3 equals log base 2 of 8, and that's because 2 to the power of 3 equals 8. It's just another way to write that exponential equation. So 2 raised to the power of 3 equals 8. It can just be rewritten as 3 equals log base 2 of 8. Therefore, log base, here's a, of x is the exponent you put on a to get x. A logarithm is just another way, we've established that a logarithm is just another way to write an exponential equation. So the equation b to the power of y equals x, pardon me, can be rewritten as y equals log base b of x. It should be noted that the precise definition of a logarithm is y equals log base b of x if and only if b to the power of y equals x. That is the precise definition of a logarithm. And since b is the base of the logarithm, b must be greater than 0, and it can't equal 1. So let's say for another example that b equals 4, y equals 5, and x equals 1024. We would rewrite, well, just what we have here. The base is 4, the exponent is 5, and x is the exponential expression. So what we have here is b equals 4, y equals 5, x equals 1024. We'd rewrite that as 5 equals log base 4 of 1024. And who invented this concept? It was invented by a man named John Napier. Hopefully I'm pronouncing that right. John Napier. And he did this to simplify tedious calculations, introducing them in his work, The Description of the Wonderful Canon of Logarithms in 1614. The main purpose behind logarithms was to simplify complex and tedious calculations. Adding numbers is a lot easier than multiplying numbers whenever you don't have a calculator. Whenever you're just adding numbers, it takes much less time than multiplying numbers. Imagine doing that without a calculator. I would not be able to do that, ever. And according to one historian, according to Wikipedia, one major historian noted that his logarithms turned multiplication into addition. It was a wonderful trick that revolutionized computation. And also, according to Wikipedia, this has been called one of the greatest scientific discoveries the world has seen. But what about natural logarithms? A natural logarithm is a logarithm to the base of Euler's number. It's about 2.71827, etc. And the natural logarithm is just a logarithm with the base of Euler's number. So the natural log of a number is the logarithm to the base of Euler's number. So the natural logarithm of x is the inverse of Euler's number to the power of x. The natural logarithm of Euler's number to the power of x equals x. And Euler's number to the power of natural logarithm of x equals x. So Euler's number and natural logarithms are they're fundamental in mathematics. They appear in growth models, in calculus, and continuous compounding in finance, and etc. But why are these concepts important? See, logarithms were groundbreaking because they turned hard multiplication problems into easier addition problems. In a world before calculators, this was a game changer for scientists. They could compute products, divisions, and powers by just adding and scaling values from log tables. And this accelerated progress in astronomy, navigation, and engineering at the time. The fact that logarithms turn multiplication into addition and powers into multiplications is the reason we use logarithmic scales to compress large amounts of data. For example, a logarithmic scale can represent values from 1 to a million in a compact way since each power of 10 is an equal step. And another reason they're important is that Euler's number and natural logarithms show up everywhere in math. For example, the derivative of Euler's number to the power of x is itself, meaning Euler's number to the power of x is its own rate of growth. So an application of these concepts in the real world, one of these applications would include compound interest in finance, something virtually all of us are going to experience at some point, if we haven't already. So the growth of an investment under compound interest follows this pattern. In this equation, A of t is the amount after t years, P is the principal, which is the initial deposit, R is the annual interest rate as a decimal, N is the number of compounding periods per year, and T is the time in years. And if the bank compounds interest infinitely often, we would say that the interest is compounded continuously. So we would use the limit definition A of t equals principal Euler's number rate multiplied by time. And this formula gives us a connection with the fundamental constant in mathematics. This formula is interesting since we now include Euler's number. It came from observing how money grows under increasingly frequent compounding. And how does that get us into logarithms? Well, logarithms answer time-based questions like how long will it be until my money doubles? How long will it be until my initial amount doubles? So we would use the compound interest formula. So let's just assume it compounds annually. So n is going to be equal to 1. So 2p equals p 1 plus rt. So we would just get rid of that 2, 1 rt. And to solve for t, we would have to take the logs. The logarithm of 2 equals t multiplied by the logarithm of 1 plus the rate. And then we would get t equals the log of 2 over the log of 1 plus r. In this equation, the logarithms undo the exponent, and that isolates t. So in the continuous compounding scenario, 2 equals Euler's number to the power of the rate times time. So that means that the rate times time equals the natural log of 2, meaning that time equals the natural log of 2 over the rate. And this pops up in a lot of financial applications. Could help us determine how fast an investment grows, how long it would take to pay off a loan, or how interest rates compare over different compounding frequencies. And a good way to visualize exponentials in finance is to compare simple interest, where you only earn interest on the original principal, to compound interest, where you have an exponential growth. So simple interest would have the formula A t equals p 1 plus rt. That's a linear increase, whereas compound interest is p a to the t a of t equals p 1 plus r to the power of t, assuming 1 year for simplicity, which would be a curved increase, meaning it grows faster and faster over time. And again, this is simple interest. And this is compound interest. And the reason this matters in the real world is that with low interest rates or over short times, that exponential growth isn't going to look like much starting off, but given enough time, compound interest can result in a larger, like a much larger balance than what you originally had, like a snowball effect.